Netherlands, where she got her undergraduate degree, and then moved to North Carolina, where she got her PhD in astrophysics, and then was a postdoc at the Carnegie Institute in Washington as a Carnegie Fellow and a Hubble Fellow. Moved back to Spain for a couple of years, and then, how many years ago? 4?
4 years.
4 years ago, missed the United States and came back to the Harvard-Smithsonian Center for Astrophysics, where she's been since. And she studies exoplanet atmospheres, and today will be telling us about breaking through exoplanetary atmospheres. So, thank you.
Yeah, thank you, Greg, and thank you, everybody, for coming. Even though I've been in this country for about 15 years, I realize I have a thick accent. So if there is something that people don't understand, please ask me along the way or at the end or afterwards, and I'll be happy to clarify or translate it into English for you. So I realize that not everybody here works on exoplanets, and so I'm going to try to give you an overview of where we are in this field, which is actually, we are at a very, very basic stage because the field is only 20 years old. And in particular, the part of atmospheres is less than 10 years old. So I will try to give you an overview of where we are, but just keep in mind that this is very new, and this is quite exciting. And there is many ideas, both in physics and astronomy and geology and biology and so on, that can be used in this field. So if you have any crazy idea after this talk, let me know, because we might be able to use it. So in any talk about exoplanets, you have to start with a little bit of statistics about how many planets we have to date. And that's just to give you an idea of where we are in this field. The first exoplanet discovery was in 1995, which I think is out of the plot there. And since then, you basically realize that was only 20 years ago. And since then, the field has made a lot of progress, and we have now about 3,500 planet candidates. Most of them have been discovered in the past 5 or 6 years after we launched this mission called Kepler that you're probably familiar with. Of those 3,500 candidates, the reason why we call them candidates is because we only know that they could be a planet because of the little dip that they produce when they cross in front of the star. So that's called a transit. It's like a little eclipse. But we don't know what the mass of the planet is. And we don't know if some other astrophysical effect could be producing those little dips. So the way that we confirm the planets, or one of the ways that we confirm the planets, is by measuring the mass of the planet, by looking at the Doppler shift. And using that technique, we have measured the masses and radii of about 500 planets so far. So we have about 500 confirmed exoplanets so far. And what I've done here, basically, is to plot them by the year of discovery versus the mass of the planet in Earth masses in log scale. And then the size of the circle gives you an idea of how big the planet is. And the bigger ones are Jupiter mass planets, and the little ones are Earth mass planets. And the color gives you an idea of how hot those planets are. So anything that is green or yellow or red and so on, those are hot planets, and they are usually what we call gas giants, which are like puffy planets. If you try to step on it, you sink. And the ones that are dark blue, those are what we call rocky planets, basically meaning that they have a solid surface that if we were able to get there, we should be able to walk on the surface of that planet. This orange line across the plot is the Earth, the mass of Earth. So as you can see, as of about 2 or 3 years ago, we have already detected planets that are like Earth, in a sense, but they really are not. And the reason why we think that they are not is because they are too close to their host, to their star. So even though they are rocky planets, the temperatures on those planets are about 2,000 to 3,000 Kelvin. So if you can think of any organism that can survive those temperatures, I can't think of many. So that's why we say that we haven't found anything like Earth just yet. So from this plot, you can imagine that over the last 20 years, we have come a long way. And finding another planet, it's not a big deal anymore unless you find a planet that is just like Earth, right? So the next exciting thing in this field is to try to figure out how those planets are, what they are made of, how their atmospheres look like, and so on. And that's the kind of stuff that I've been working on for the past few years. Next, I'm going to describe to you what an exoplanet scientist think of an atmosphere of a planet. If there is any planetary scientist in the audience, I apologize, because from us on Earth, looking at exoplanets, we can detect some properties of the exoplanets, but they're very limited. I mean, these are not like the solar system planets where you can send a probe and go through the atmosphere. We are just looking from afar. And there's only a few things that we can observe, but those things I think are key, and they're going to give us, and they're giving us already, like very, very nice and key information. So the definition of an atmosphere from an exoplanet point of view is basically we have two types of planets. You have rocky planets, and you have gaseous planets. In the case of a rocky planet, it's very easy to define an atmosphere because you have a solid surface. So the atmosphere is a little thin layer on top of that solid surface. And the way that we define an atmosphere is by these 4 parameters here, because those are the parameters that we can measure. The chemical composition of the atmosphere, the average temperature, wind speeds, and bond albedo. For those not familiar with what the albedo is a parameter between 0 and 1 that we define to get a sense of how reflective the atmosphere of the planet is. And basically, that gives you an idea of the cloud coverage. If the planet has clouds, then the light coming from the star is going to get reflected. If the planet doesn't have any clouds, then the light just goes through. So if you have a planet that is fully covered by clouds, you should have an albedo of 1. That means that all the light coming from the star gets reflected. If you have a planet with a perfectly clear atmosphere, the albedo is 0. There's no reflection. So that's the kind of stuff that we can measure. And as you can tell, in the solar system, we have basically 3 rocky planets, Earth, Venus, and Mars, and Mercury, of course. And even though those 3 planets are very similar, from the atmospheric point of view, they are quite different. And you can see the chemical composition, for example, in Mars and Venus, the atmosphere of the planet is dominated by carbon dioxide, while in the case of Earth, we have very low carbon dioxide, and we have a lot of nitrogen, second by oxygen with 20%. Temperatures are very different as well, especially between Venus and Earth. And that's just not only because Venus is closer to the sun and it gets irradiated more than the Earth, but also because of the greenhouse effect that is going on in Venus. And then you have wind speeds that are similar, and albedos that you see, like Venus, as you probably know, is almost fully covered by clouds. So it has a very high albedo, while the atmosphere of Mars is very thin, and it has barely, very little clouds and hazes, so it has fairly low albedo, and the Earth is in between. So what you see from here is that even planets in our solar system that are rocky planets and are similar in mass and radius, from the atmospheric point of view, they're totally different. Then the second class of planets that you have is, is the gas giants, the gaseous planets. But from the atmospheric point of view, they're basically the same thing. I mean, you use those 4 parameters, and those are the parameters that you get. To define the atmosphere in a gas giant is a little bit more difficult because you basically don't have a solid surface. But as you go inside the atmosphere, eventually the density goes higher and higher, and it becomes like liquidy. But there isn't like a difference between atmosphere and the rest of the planet. But from our point of view, the parameters are the same. And as you see, in the case of the giant planets in our solar system, most of the atmosphere is composed by hydrogen. And this is because the gravity in these planets is higher. So even the light atoms, their escape velocity is not large enough to counteract the atmosphere of the planet. So the small planets have lost the hydrogen and the helium. The big planets actually keep it. And then, in terms of temperatures, they're a little bit cooler because they're farther away from the sun. The speeds of of the wind. I mean, they're really high in some of the planets, and this is not even understood for our solar system planets. Some people think it's because of thermal emission coming from the interior, and because there isn't any surface to slow down the winds, so those winds build up. But as a theory, it has not been proven yet. And then in terms of albedo, most of them have an albedo that is similar to the albedo on Earth. So that's the kind of stuff that we can do, and those are the kind of parameters that we can observe. But now the question is that even when you look at the solar system, I mean, we only have 8 planets, and they're so diverse, they're so different. Like even the planets that could be similar, like Venus and Earth, they're so different. So the question is, how do planets, out there around other stars look like? I mean, do they look like planets in the solar system, or are they a completely different zoo? Which that's what my guess is. Until recently, we haven't been able to do this. Until in 2009, the Kepler mission, the NASA Kepler mission flew, and they started observing, or actually discovering, all these planets. So we have now many, many planets with which we can do statistics on the atmospheres, and that's what we are trying to do. So the way that we're trying to do this is basic and sophisticated at the same time. We basically have 3 different techniques to try to do this, and I will try to explain to you what the techniques are now, to then move into what I think is the key way to observe the atmosphere, at least with telescopes from the ground. And I will explain I will spend the rest of my talk on that part. But first, I'm going to explain to you the 3 ways that we are observing the atmospheres of planets. The first way is what we call transmission and emission of transiting planets. So basically, the idea here is that you have planets going around the star, and at certain angles from Earth, the planet goes in front of the star and it goes behind it. So when it goes in front of the star, you have the atmosphere of the planet, and part of the light coming from the star passes through the atmosphere and interacts with whatever atoms or molecules are in the atmosphere, and the spectroscopic signal of those chemicals get imprinted in the light from the star. So what we do is we observe the planet, the system, before the planet goes in front. So that means that you only get the light coming from the star. We observe it when the planet goes in front, and we observe it afterwards. So if you subtract the light from the 2 points where the planet is not going through the star, in front of the star, from that spectrum there, you can get the spectrum of the atmosphere of the planet itself. So that's what we call transmission spectroscopy. When the planet goes behind, it's the same idea, but in this case, you lose light, and you lose the light that the planet is emitting. So if you measure the system before and after eclipse and during eclipse, and you subtract the outside from the inside, you're left with the emission from the planet. That's one of the techniques, and it's actually the most successful technique so far. There is other ways to do this, 2 other ways, more specifically. One of them is called phase curves, and basically this is the same case of a planet that is going in front of the star and behind. And what we do is we observe the system throughout the whole orbit. And as you see, as the planet is rotating, one of the sides of the planet gets illuminated, and the amount of surface that gets illuminated changes. So as you monitor the system, you see a change in the amount of light from the surface of the planet. And when the planet goes behind the star, you see a little dip. And when the planet goes in front of the star, you see a bigger dip. So those are the transits and the eclipses there, and that's the phase curve from the changes in the phase of the planet. So that's technique number 2. And the mother of all techniques, but this one is still in the process of being developed, but we will get there in a few years. It's called direct imaging. Basically here, what you do is you use this thing that we call a coronagraph. That is basically a plate that you put in the front of the telescope or somewhere, in the path of the light, and you block the light coming from the star. So if you block the light coming from the star, you can see the little planets that are around somehow. And then, if you place a slit here, you can disperse the light. So here will be the star, and that will be a planet. And this is actually a real data set. This is not a simulation or anything. If you place a slit here, you can spread the light into different colors, and you get a spectrum. And that's how you can measure the composition of the planet and so on. So these are the three techniques that we use. And there has been a few results using these techniques that are really cool. But my two favorite ones are these two that I'm going to show to you now. The first one was the detection of the transmission spectrum. Remember when the light goes through the atmosphere of the planet? Of this planet called GJ1214b, which probably does not tell you much if you don't work in this field. But these type of planets are what we call super Earth, that are in between the mass of Neptune and the mass of Earth. And there isn't anything like this in the solar system, but they seem to be the most abundant type of planets, like at least in the galaxy. And so there is a lot of interest on observing the atmosphere of that planet. And Laura Kraber's group observes this planet with the Hubble Space Telescope at around 1.4 microns. So this is in the near infrared. And if you look at the lines, the purple and the orange-yellow lines, that would be how planets with a lot of methane and a lot of water would look like, the spectrum of the planet. But instead, they find something that is totally flat, and those are the white data points. And this, at the time, was a little bit frustrating because the fact that the spectrum is totally flat, what it means is that the atmosphere of that planet is really cloudy. So the light does not go through. And there has been a few other observations like this, and we are finding clouds everywhere. So we are now, at least for that particular type of planets, we are now at this standpoint where we don't know if we're going to be able to do this at those wavelengths, but we have the James Webb Telescope coming through, and hopefully once you get into the infrared, you can see through the clouds, and we will be able to get more information. But this has been a little bit of a disappointment right here. Oh, and I forgot to say, I know that there is some cosmologists in the audience, so I thought that this was an interesting piece of information. To get this data set took as much Hubble Space Telescope time as to image the Hubble Deep Field. Just to give you an idea of how crazy this is. So this is one result that I thought it was quite cool, although a little bit disappointing. This other result here is my favorite. So this is a phase curve. Remember what I was telling you, like the portion of the surface of the planet that you see changes as a function of the orbital position of the planet. So if you monitor it, you see the different size of the planet, right? So this is done with the same instrument, but what they did was they monitor the planet over the orbit. And what you see down here is a simulation of how the surface of the planet changes with phase at two different wavelengths. So you see that one side of the planet is very hot, and the other side is very cold. And that on itself, it tells you that there isn't a lot of winds going around, because otherwise the whole surface of the planet would be about the same temperature. And another thing that you can see here is when you're looking at the bright side, you see that's the spectrum of water absorption. And when you look on the dark side, the water absorption goes away. So what that means is that in the hot side, the planet is hot enough to have water in vapor phase. And in the dark side of the planet that is too cool, the water has condensed out of the atmosphere, and that's why you see water and you don't see it as you go, as you change in phase. So that's another really cool result. All the results that I have shown to you right now are from space with the Hubble Space Telescope. But the problem that we have is that the Hubble Space Telescope is a 2.5-meter telescope, which doesn't collect a lot of light. We have the James Webb Telescope coming hopefully online in 2 years. But But that's only one, it's bigger, but it's only one telescope, so there's only so many planets that you can do. And the problem that we are facing in this field now is that we don't have enough instrumentation in space to do this kind of science. I mean, to get to the point where we have a statistically significant number of measurements of many planets, to be able to come back and tell you, well, every Jupiter looks like our Jupiter, every Saturn looks like our Saturn, or whatever the answer is. So to be able to accumulate that statistical, amount of observations, we need something else. And what we need is to move these observations to the ground. Because in the ground, we not only have a few 8 to 10 meter telescopes, but we also have 3 extremely large telescopes coming online, hopefully soon. And so this is the reason why me and another few people have been trying to develop this technique from the ground that can basically do the same measurements that space observations do. Basically, what I mean is we can measure chemical composition, we can measure winds, we can measure temperature, and we can measure albedo. And in addition to that, this technique gives you the mass of a planet even if it is not transiting. And we're thinking of ideas of how to measure the radius as well, and I will show to you all that now. So the rest of the talk is going to be focused on this technique, which is the future. This is the future for you. And at the end of the talk, I will show you how we are going to try to apply this technique to detect oxygen when we finally find the first Earth-like planets. So the technique that I've been talking about for a while is high-resolution spectroscopy. So you basically need a resolution of about 30,000 or higher. And for those that are not familiar with spectroscopy and talking about resolutions and so on, basically what this means is that you have to spread the light so you can separate wavelengths within an interval of delta lambda. So basically, a resolution of 35,000 in the optical means that you can isolate wavelengths in a step of about 0.7 angstroms. So that's just to give you an idea. So the higher the resolution, the more detail you get in the spectrum. So this is a high resolution technique. You can do it from the ground with telescopes that we have right now. And a lot of people have been trying to do this from the ground with other techniques. And there is a lot of, and excuse my French, but there's a lot of crap out there, like including my own papers. Like there's so many systematics that it's just crazy. But this technique allows you to overcome those systematics, so it works really nicely, as you will see. And then, as I was telling you before, with this technique, you can also measure the mass of the planets, even if they're not transiting. So that's a big plus. So to explain to you this technique, let's go back to Astronomy 101. I hope everybody took Astronomy 101 back in the day. So basically, an exoplanet system is a binary system. And you saw binary systems, I'm hoping, right? So you have 2 stars going around each other, and they orbit around the center of mass, right? So this is Kepler's laws. So you basically, what you have is you observe the system, and you see the light of one of the stars blue shifted as it comes towards you, and the light of the other star red shifted as it goes away from you. And from the blue shift and the red shift, you can measure the amplitude of the radial velocities. And then from the amplitude, you measure the mass of the stars. And if you're lucky and they are eclipsing, you can also measure the radius. But in this case, we only need to measure the masses. So the idea here is that in a binary system, you have maybe 2 stars, so they're like 1 solar mass and half a solar mass, right? In a planetary system, you have a binary system where the second star is 1,000 times less massive than the first one. But it's the same, right? It's the same physics. So what you have is basically, and I highlighted that here, what you have is Kepler's laws. So what we have to do is somehow, we have to measure the velocity of the planet. And measuring the velocity is quite easy because since the difference in mass is so large, the center of mass is really close to the actual star. And that's why you have heard, oh, astronomers have this technique that measures the wobble of the star, which has an amplitude of about a few meters per second. But because the center of mass is so close to the star, at the same time, the planet doesn't move at meters per second, it moves at hundreds of kilometers per second, just zooms around the center of mass. And kilometers per second, we can measure that stuff, like easy peasy. Now, the trick is the signal of the planet. You can measure a Doppler shift of 100 kilometers per second, no problem. The key is that the signal from the planet versus the signal from the star is a factor of 10 to the minus 4, 10 to the minus 5. That's where it gets tricky. So we had this idea from, I don't know, like 10 years ago, but we just couldn't figure out how to detect the light coming from the planet to measure the Doppler shift. And in 2010, Inya Snellen published this paper in Nature, and that was like, wow, that was like an eye-opener. And what he did, I mean, he obviously was thinking about the same thing. So what he found was the way to measure the Doppler shift. And the way to measure the Doppler shift, and this is the smart part of the whole thing here, is that he figured that at the temperature of these Jupiters, because I mean, we have only done this for Jupiters so far. So these Jupiters are pretty hot. I mean, they have temperatures of about 1,500 Kelvin, 2,000 Kelvin. So he realized that there was carbon dioxide in the atmosphere. And in any molecule, you have the rotovibrational stages of the molecule. So the spectrum of the molecule looks like a lot of lines like that. So if you have very high resolution, you can measure the lines. And because the planet is moving so fast, those lines are Doppler shifted. And the Doppler shift changes a lot. So what did he do? He went and said, well, I know that there's a carbon dioxide band at 2.3 microns in the infrared spectrum. And if I sit in this planet for long enough, I will be able to see the Doppler shift of the carbon dioxide line. And he does this by taking a template of a carbon oxide molecule and cross-correlating with the spectrum of the system until he finds a match. And I will show that to you. This one is a little bit more technical, but it's basically the same idea. So what you do is you observe the planet as it goes around the star, right? And at different positions in phase, the planet is going to have a different Doppler shift. So what you do then is you take your template of carbon dioxide and you try to cross-match it. And at the speed that cross-matches the carbon dioxide from the planet, you see a peak in the cross-correlation function. So what he did here is to go and say, okay, so this is velocity, the Doppler shift, and this is orbital phase. So basically, this is how he observed over time. And this peak here is the cross-correlation peak. So this is basically, if the cross-correlation peak looks like that, if you take that plot and turn it like this, that will be your peak there, right? So that's what he sees. And he observed this for HD 209. That was the first transiting planet discovered back in 2000. And he not only observed that there was carbon dioxide in the planet, but he also observed a Doppler shift of the whole thing of about 2 kilometers per second. So that was the first detection of wind in an exoplanet atmosphere. So that was cool as well. So with that idea in mind, we actually said, well, okay, so let's see. Oh, and I forgot to say, HD 209 is a transiting planet. So we already knew the mass. And so the technique actually confirmed the same mass as well. So we knew that the technique worked. So the first thing we did was like, oh, this is so cool. You know, Snellen found a way to do this. Let's try to do it in a non-transiting planet. And let's try to see if we actually can measure the mass of a non-transiting planet. So we did that. And we went for this planet called Tau Bootis, which is down here. So it's that little star. This is a 4th magnitude star, so you actually can see it with an naked eye. And this was the 3rd exoplanet discovered ever in 1996. So when they discovered it, they found that it had an orbital period of 3.3 days. And let's see, down here, they gave a mass of the planet times sine of the inclination of the system of 4.1 Jupiter masses. But this is not a confirmed planet, because if the inclination is 90 degrees, the mass of the planet is infinite, right? Or infinity. So that could have been a system with very low inclination, and the second star or the second object not be a planet, but like an M-dwarf star, like a little star. So we went ahead, and following this technique, we observed with the VLTs in Chile, resolution of 100,000, 2.3 microns, and we were looking for the carbon oxide. So we monitored the system between phases 0.5 and 0.6. So that's just a portion of the orbit, just to not make it complicated. And this is not what we saw. If I show you the real data, you will probably cry. But this illustrates the idea of what we were looking at, right? So here, as vertical lines, you have a combination of the lines from the star and the lines from our own atmosphere. So just to give you an idea, this is phase, so that's equivalent to time, like when the planet is at a different position in the orbit. And this is just wavelength, which is equivalent to Doppler shift, right? If you shift it in wavelength, you shift it in velocity. So if you see, you probably notice that all the lines that are coming from the star or our own atmosphere, they don't change. But you probably have noticed that there is these lines here, right? And those are the carbon oxide lines that change in Doppler shift as a function of time. So we observed in that phase interval here. And when you do the cross correlation with the carbon oxide template, this is what you see. Okay, so this was our data set here, which, if you believe that signal, oh my God, we actually had a hard time believing it. But when you bring that image and you put it like sidewise, that's the peak of the cross correlation there. So we were able to see that the planet moved with an amplitude of 47 kilometers per second. And based on the amplitude, we could set up an inclination for the system of 44 degrees. And that gives you the exact mass of the planet. That was about 6 Jupiter masses. So we confirmed that this was a planet indeed. And at the same time that we were doing this, completely independently, this other group actually had much better data than ours because they had 3 nights of observations with the same telescope, same instrument. They saw the exact same signal. So you see here in the 3 different nights. And they measure an inclination of 47 degrees, which is consistent with ours, and a mass for the planet of 5.6 plus minus 0.7, which is also consistent. So this is the way that science should be done. Like 2 different groups, they aim at the same thing without even knowing that the other ones were doing it, and we both find the same result. So this was the first time that we could directly measure the mass of an exoplanet that is not transiting. And we could also tell you that there was carbon oxide in that planet. So we have tried this with another few planets, looking for carbon oxide and water, because water also has that molecular band shape in the spectrum. We have also looked for methane, but we haven't found any methane yet. And basically, these are the results so far. We have these 2 planets which are transiting, and the reason why I highlight them is because since they were transiting, we knew already what the inclination of the system was, so we already knew what the mass of the planet was. So we find pretty much the same mass as they had found with the wobble technique, and we searched for carbon oxide. So we found carbon oxide on that one. On this one, we have carbon oxide and water, and then these other 3. This is the one that I just showed to you. We have found carbon oxide and water, and carbon oxide on that one. This was the first planet ever discovered. So we measured a mass for it of half a Jupiter mass, which did not have a mass either after 20 years. And we also have carbon oxide and water for this one. So this is all that we have done so far. And now we're stuck. And the reason we're stuck is because if you're familiar with the magnitude system, small numbers means brighter stars. So far, we can only go down to about 8th magnitude. And that's fairly bright. Like with a naked eye, you can see stars at 6th magnitude. So we're stuck because we need bigger telescopes to do these kind of observations. Like anything fainter than 8th magnitude, the telescopes are not big enough. So we need the next generation of telescopes to continue doing this kind of science. And then, at this point, I also must say that this technique sounds wonderful, But it does have one limitation, like any other technique. We all have some problems, and the limitation of this technique comes in this column here that I'm showing to you. So as you see here, I'm showing to you line contrast. That means like how deep the lines are when we do the cross correlation. But notice that I'm not talking to you about abundances of the actual chemicals or molecules. And the reason for this is that, I'm going to try to show this to you. This is a little bit complicated, but yeah, I'm going to try to simplify. So this is a transmission spectrum of one of those planets, observed all the way from the infrared to the optical, using the transmission technique from space. So that gray line here would be how the atmosphere of the planet would look like if it didn't have any clouds. But you see that instead we see that Rayleigh scattering slope, and down here seems to be quite flat. So that means that that planet has a lot of clouds on it. And we know that from this observation. So when we use the other technique, the high resolution technique, you detect carbon oxide here, but there is plenty of clouds there. So basically that means that you are detecting the carbon oxide that is peaking on top of the clouds, but you have no idea how much carbon oxide you have underneath the cloud or within the cloud. And that happens for every chemical or like for every molecule. So the limitation of this technique is that you cannot get absolute abundances. I mean, you know that there is some molecule there, but you don't know how much. So that's the limitation. I mentioned this at the beginning, and this is stuff that we are working on. It's not published yet, but this is also quite cool because if this technique works, we can also measure the radius of non-transiting planets. And the idea that we have is that based on the phase curve that I was telling you about before, when you monitor the system in phase, from the amplitude of the variation in brightness of the system, you can guess how bright the one side of the planet is versus another. And then you use this equation here that I will try to explain to you. So this is delta Fp is the amplitude here normalized by the average flux coming from the planet. That would be like a line in between. And you know that that amplitude is the difference between the black body emission from one side of the planet versus the other side, divided by the emission of the star itself at that particular wavelength, times the radius of the planet over the radius of the star, times sin I. So basically, to make the story short, you know everything here. The radius of the star, you can measure it using interferometry. If you can measure the sine curve, the phase curve, sorry, you might be able to measure the radius of the planet. But this is something that we are working on. We haven't published it yet, but if this works with this technique and with the high resolution technique, where you can measure the inclination of the system, and phase curves, we might be able to just tell you the mass and radius of planetary systems, or the planets, without having to transit or anything. Just any planet in the universe, as long as we can detect the signal from the planet, we can tell you what the mass and the radius is. Ah, you got me. Yeah. So basically, what we are saying is that, and that's the one assumption that we are. That's why we haven't published this, because we're still thinking about this. We're assuming that half, like the planet is like two halves of an orange, a cold one and a hot one, and we're assuming that they emit as black bodies, which is not true. So that's the one. That's the one assumption, and that's the one that we're still trying to convince ourselves that that's reasonable. So yeah. You got it. Okay, so this is a technique. This is where we are right now. This is what we're trying to do. And in the future, hopefully in the next decade, our idea is to apply this technique to detect oxygen in Earth analogs. And I just wanted to put up this photo because I love this photo. So oxygen is what we call a biomarker. meaning it's a signature of life. And on Earth, we know that there is oxygen because there's life on Earth, right? Like other things like methane, carbon dioxide, that kind of stuff, you can produce it via other sources. And there's some people already saying that you can produce oxygen via other sources. But for us, just for now, oxygen is a sign of life. So that's the reason why we want to go for oxygen. And so that was the little thing. And so right now, we have no way to do this because we don't have another planet like Earth. And but in December 2017, unless things get delayed, there is this NASA mission called TESS, the Transiting Exoplanet Survey Satellite, that is going to be launched, and it's going to observe all the stars in the sky, or most of them, and especially the bright stars that are close to us. So based on these simulations by Sullivan et al. Last year, they predict that there will be about 70 planets coming out of TESS that are going to be just like Earth. And by just like Earth, we mean at the right distance, the right size, and the right mass. So they're going to be what we call in the habitable zone. So as I showed you at the very beginning, Venus and Earth look very similar, right? So even if you have those 70 planets, how do you know that they look like Earth? So one way to do it is with oxygen. The technique that we are going to use is the transmission spectroscopy technique that I explained to you at the beginning. The test planets are going to be transiting, so we can look at the light going through the atmosphere of the star. So that's already solved on how to do it. And then the way that we're going to do it is we had to identify an oxygen band on Earth, right? So the trick here is that we're going to do this from the ground, and we're going to try to find a planet that is an Earth twin. So you might be wondering, right, if you have an Earth twin, then that's how the atmosphere of the Earth looks like. And those, the yellowish bands, that's water, and the cyan bands, that's oxygen. And this is low resolution. If you increase the resolution, this is how the molecule of oxygen looks like. So it looks similar to the carbon oxide. So you understand now why we can use the same technique, right? And the problem, well, yeah, we have two problems. The first problem is that in the case of the big planets, to look for carbon oxide, the contrast between the planet and the star is of the order of 10 to the minus 4. In this case, the contrast is of the order of 10 to the minus 6. So we cannot do this right now. But at the CFA, we are part of the Giant Magellan Telescope Consortium, and we're also building this high-resolution spectrograph called GCLIF. And this is going to be the main science case for this instrument on that telescope. And as I told you before, we are going to aim at the oxygen band at 0.776 microns. And the trick, again, is that because we are looking for the atmosphere, you have our own oxygen band. But the oxygen band from the planet is going to be Doppler shifted. And it changes, right? While the oxygen band from our own atmosphere is steady. It's going to be there. It doesn't change. So this one changes. So obviously, right now, we don't even have a candidate to observe. We don't have a GMT. We don't have a GCLIF. So the only way for me to show you if this is going to work or not is by doing these simulations that we did a couple years ago. And so that's the oxygen band that we have. This would be our own oxygen band from Earth. So as you see, it's much stronger. And then we model this for many different types of stars, like from stars like the sun to the very little M dwarfs, like 0.1 solar mass stars. And we model it for systems all the way from 0 to 100 parsecs, and we did all these simulations. And this is what we find. The first thing that we find is that the system is going to be moving with respect to us. So not every planetary system is going to be doable because the oxygen lines from our Earth and the oxygen lines from their Earth are going to overlap at some velocities, right? At some some of the Doppler shift. So if that system doesn't move with respect to us, we have no chance. But then the part that we didn't expect is that if the system is moving at plus minus 50 kilometers per second, then this line overlaps with the next line in the oxygen spectrum, and we will not be able to see those systems. So let's see how we can figure that one out. I mean, one way to do this is to wait half a year, you know, when our, what's the name? The barycentric velocity of Earth has changed, so this might help, but we need to think a little bit more about this. And the second thing that we did, is to estimate for which type of stars we would be able to see this. And what we find is that for a star like the Sun, with an orbital period of 1 year, you would need many transits to do this kind of observations. Actually, you would need 37 transits. And the problem with like a true Earth analog is that it would take us 37 years to collect enough data. Because as you can imagine, if you have a planet like Earth orbiting the star once a year, you can only catch the transit once a year. So to collect enough photons to be sensitive to the oxygen signal, we have to wait 37 years. But as you go down on the mass of the star, the habitable zone of the planet gets closer in. And then you have that the transits actually occur more often. And the more often you occur, the more that you can catch in a year. So there is an optimal peak for stars of spectral type M4, which is about half, like 0.4 Earth masses, solar masses. Sorry, it's almost 5. I'm getting tired now. So these stars are about 40% the mass of the Sun, and they have a planet in the habitable zone of this star would be at a distance, at an orbital period of 26 days. So it would take still like a significant amount of transits, but you could do this in only like 2 years, because you can catch like more than 10 transits a year. So this is the numbers that we have, and still it is going to take a significant amount of time on a big telescope, but this science case has become the main driver, at least at the CFA, for building the Giant Magellan Telescope right now. So I think I'm right on time. This is everything I wanted to show to you. I'm getting tired, so I understand that I might have been like going through things a little bit quickly, but I will give you the summary here, and I will answer as many questions as you want. So basically, the main points that I wanted to bring to you is that we are now at the stage where we are not just finding the planets, but we're trying to characterize the atmospheres. And we're trying to see if these planets are similar to the planets in our solar system, if there is true Earth analogs out there. So we're actually finally, at least from my point of view, we're finally starting to do physics, in exoplanets. We have found one technique to do observations from the ground that will be able to use the very large telescopes, and therefore, it's going to increase the productivity of the field. We are not relying on space telescopes anymore only, and this is the high resolution spectroscopy technique. With that technique, we can detect all the parameters from the atmosphere that I mentioned to you before: composition, albedos, temperature, and winds. And we can also measure the mass and hopefully the radius of planets, even if they're not transiting. This is what I just said to you, that we can measure all those other parameters as well. And then the best part of this is that hopefully we will be able to use this same technique to detect the atmospheres of Earth twins once we find them. Thank you, and I'm open to your questions now. The temperature regime that we're playing with. So in the case of the water detections, those have been done on Jupiter, and they are at temperatures of 1,000 Kelvin or higher. At those temperatures, molecular oxygen is not stable. Molecular oxygen is only stable at about 300 Kelvin. So they're totally different systems. So the technique is the same, but we have detected water in Jupiter's, and molecular oxygen is in the small planets. And another thing, I've been trying to do the simulations for the water in the small planets, and what happens, and this is, I mean, it's opening my eyes to so many things. What happens is that in the Earth's atmosphere, the water is concentrated in the first 10 kilometers. And for systems like this, because we are looking from very far away, when the light from the star goes through the atmosphere of the planet, it suffers from refraction, because it's a Snell's law. So you have vacuum with a refraction index, and then you have the planet with a different refraction index. So for the first 10 kilometers, we cannot see photons going at that height because they get refracted away. So even if the planet has, if the Earth analogs have water, we are going to have a hard time detecting it. So, yeah. But anyway, so your answer is that the water has been detected for the Jupiters. Oxygen is not stable at those temperatures.
And the second, simple question, why is the mass of the planet important parameter?
Because that's the only way that you can tell if you have a gas giant or if you have a rocky planet. Because the mass combined with the radius gives you the density. It's mass over the radius cube. So that's why. It's a density. But you need both. Yeah. Yes. Detect. Yeah, we just last week we were talking about this, and we were wondering if we could detect Zeeman splitting in some lines that are sensitive to magnetic fields. I checked this up, and the Zeeman splitting for Earth is 40 kilometers per second. So in principle, yes, we could detect this. The only thing is, the only problem that I can think of is that because of the signal of the planet is so weak, our template has to be sensitive to just 3 lines. Because one thing that I didn't say is that the advantage of this cross-correlation technique is that you have so many lines. So in this case, we would have to have 3 lines. So that yeah, but then you only have like a very narrow part of the spectrum that is sensitive to Zeeman splitting, for example. We have been thinking of Zeeman. I don't know if there is something else that we could look at, but that's one of the questions that, for physicists, if you guys have ideas like that, it's like they're more than welcome, because we're so open now to everything that we just don't know what to do. I mean, it's not that we don't know what to do, but I'm sure that we're thinking of things, that there is ways to do it, but this is not what we do for a living. So, yeah. Nah. Yeah, we do. We actually, I have another talk that I didn't bring. Somebody did a simulation of the planetary systems. So there is one system with 7 planets, and there's another one with 5. But they're all within the orbit of Mercury. So there's many, many planets, but they're all like really close in. Look, it's a zoo. I'm telling you right now. The solar system is an oddball among these things, because you have like, systems with like 7 or 8 planets, no, 7 or 5. Then you have some of them, you have these hot Jupiters that are like at orbital periods of about 3 days. Nobody has any idea how they got there. You have planets that are evaporating, so they have like these cometary tails that are being observed. You have the super Earth, which they do not exist in our solar system, but they are, the mass and the size is between Earth and Neptune. They're everywhere, and we don't have one in the solar system. So it's a zoo, I'm telling you. Yeah. Okay, I can tell you that we probably have not covered the parameter space, because say Jupiter is at an orbital period of 12 years. We haven't gotten out there yet. Like Kepler only observed for 4 years, so you might be right. But right now, like everything that we are finding doesn't look like the solar system because of the time scale of the observations. But at the same time, we're finding a lot of stuff that is like, oh my God, you know, like it's really cool. Yeah, so.
From an earlier slide, the albedo Jupiter is like 0.3. So, but on most of the photos, we cannot see the surface of Jupiter. Because of the halo.
Well, that's, yeah. So there is I was just talking with Ralph Millikan. You can either do the albedo of clouds. Like right now, we're only sensitive to clouds, basically. So say a Jupiter shouldn't have a surface, but it has clouds. So we know that if we see light that looks like the spectrum of the planet, of the star, it is reflected, and it's reflected by clouds in the atmosphere. But another possibility, and I was just talking with Ralph, and this might be really exciting, but it's not going to happen for a long time, I think, is if you have a rocky planet that is clear, right? So you can look through the atmosphere, you might get albedo of the surface. So you might be able to tell if there is rock, or you know, if it is a little bit reddish, you might be able to tell that it has a lot of iron. Or if it is a little bit greenish, you might be able to tell that it's olivine, that kind of stuff. But we aren't there yet. So yeah, that's a good question. You had a question as well, right? We have seen planets going around binary stars, but not one planet going around each other. No, we haven't seen that. But David Kippen, he's at Columbia University now. He's looking for moons, which would be like a little binary, right? So he's looking for moons, and he's convinced that he's going to find them. So, but yeah, no, we haven't seen any binary planets yet. Up there.
Yeah, I have one question about that. So what are the conditions of the atmosphere for different
Oh, I wish I knew the answer. That's one of the things that we don't know. We're assuming, okay, so our idea right now, but you might ask me this in 5 years and I tell you a different story because we know more. But our idea right now is that at the very beginning, when the system forms, you have the disk, right? And those disks can be more metal-rich or poor. And then in our own solar system, we know that most of the heavy elements went into the big planets, right? So I think that it depends on the initial composition of the disk, how much stuff you get in the planet, and or it depends on the way they form, whether more heavy metals went into the planets or stay in the disk and ended up in the star. Right now we don't know, but they are quite different. Yeah. They should be different. Yeah, because like say, well, at least from my astronomy classes, if you go back in time, right, wherever the gas disk was at the time, it should be more metal poor, right? So the earlier it forms, the less heavy elements you have. And even in the galaxy, you have metallicity gradients, right? If you're closer in, or is that the opposite? Yeah, if you're in the halo, you have less metals than if you're in the disk. So one thing is a function of time, a different thing is also a function of position in the galaxies. So yeah, but we don't have an answer yet. Basically, we don't know. No, sometimes. But the big flares don't start until later, like M6, M7. But they're definitely more active than the solar type stars. So that's and the habitable zone, like, I mean, the habitable planets are closer in. So that's an issue that some people have brought up, that maybe the irradiation on the planet from high energy photons and ions and stuff is so high that it rips off the atmosphere. But there is some work from this woman in Mexico, Antigua Segura, that claims that at a normal rate of flares, because the effect of the flare only affects the upper layers of the atmosphere, the rate of flares is slow enough so the atmosphere has time to recover. So there is both groups of people.